Everybody see that good? You good with that? Okay. Right, so underwater inspections. Inspection of underwater structures. So structures that are placed in water have. Can everybody hear me okay? Okay. Right. Structures that are placed in water have unique challenges for the inspection teams that maintain them. Depending on their construction and age, they can be vulnerable to changes in the environment in which they sit. Structures found in bodies of water require special monitoring to ensure that they do not become compromised by their environment. This can include wave action, fast-moving water, flood events, floating object collision, weed cutting, or dredging, even relatively distant from the structure. Designers have had to engineer modern structures for all these risks. However, there remains unexpected risks that can also compromise a structure's integrity. Well-planned and executed inspections can reduce these risks, but the inspection team will still be faced with significant challenges during severe weather events, and it's how these are managed that we'll look at more detail. All water structures must be safely managed in severe weather events. This is very difficult to achieve during the flooding event itself, because the water course becomes very dangerous to work in with dynamic, fast water flows, debris and silt. Normally, air divers are used to inspect these structures visually in good weather and in low flow conditions. During these conditions, the water is safe to enter and clear up to see any defects. This type of routine inspection is adequate for the majority of the time, but it is during the flooding events that some structures can be most at risk. When it all goes wrong, a sudden violent weather can compromise the structure in hours. And here in Workington Bridge in Cumbria, a police officer tragically lost his life, and more lives could have been lost had not passers-by intervened. And you can see from this picture, the abutment itself was undermined and washed away, and the whole bridge collapsed. Sudden violent weather can compromise a structure in hours. An inquest into the death of a police officer who was killed when the Workington Bridge collapsed during the Cumbria floods in 2014 was told today more lives could have been lost had passers-by not intervened. The hearing was told that PC Bill Barker had been directing traffic off the Workington Bridge when it gave way beneath him at 5 a.m. on the 20th of November. The 44-year-old fell 20 feet to the swollen River Derwent and was knocked unconscious by a blow to the head. He drowned, and his body was carried 8 miles away and found on a beach in Allenby the following day. And here we have a scoured, damaged masonry pier with debris adding to the scour problem. Once you start losing this as the hangman's drop, then the whole thing is compromised. So, testing and trials. So it was in 2014 that the Structures Inspections team in Highways England Area 3 and Sea-Tech Commercial Diving and Salvage began trialling the Tri-Tech Starfish, a high-resolution chirp pulse side-scan sonar unit for inspection of vulnerable structures. The new equipment had just come onto the market, and the Tri-Tech Starfish high-resolution chirp pulse side-scan sonar unit. Of course, side-scan sonar had been around for decades, but this inexpensive high-resolution could give down to 1 centimetre resolution at ranges up to 10 metres. This would mean that any defects large enough to affect the integrity of a structure would be able to be seen clearly without a diver ever entering the water. This technology was tested with research funding from Highways England on Kemp's Quay in Southampton for 3 weeks. And it was also trialled in Newcastle by Tyler Weir Marine, who produced this incredible stitched image of a dockside outfall tunnel, both above and under the water. And it is absolutely amazing. They used a multi-beam sonar to actually go into that tunnel and take more readings. So a multi-beam sonar just generates a point cloud basically. So, side scan image of a piled pier. Look at the side scan image, and at the bottom left of the image, you can see the pile cap itself becoming exposed by scour action of the river. Unchecked, this scour will start to compromise the piles, potentially cause stability issues for this substantive pier. Potential remediation here may include large single-sized stone placed around the pier or rock armour. All potential solutions have to be hydraulically modelled to ensure that it does not make the situation worse. And if you look at the little diagram next to it, you can see exactly how the scour can start. It's just a very turbulent downstream, and the eddies just can dig stuff out quite quickly. So how does chirp work? Compressed high-intensity radar pulse techniques have been used for many years above water. The techniques have been modified and adapted for use in commercial acoustic imaging sonar systems. Compression transforms a long-duration frequency-coded pulse into a narrow pulse with greatly increased amplitude, which offers good range resolution because the half-power beam width of the compressed pulse is consistent with the system bandwidth. Instead of using a burst of single carrier frequency, the frequency is swept over a broader range to create a single acoustic signature pulse. Using pattern matching techniques, the device can look for its own unique signature being echoed back from targets. And that is how it works. It's a comparison of the traditional systems and the chirp system. So the conventional Tritech system has even pulses and bandwidth, and the chirp system has a varying width and bandwidth. So the smallest pulse length is 50 microseconds, and the velocity of sound in air is approximately 1,500 meters a second. So we get a range resolution of 3.75 millimeters. The bandwidth of a typical chirp system is 100 kilohertz. And that gives us a resolution of 7.5 millimeter, a five-fold improvement over the conventional system. So at 10 meters with a Tritech starfish, we can actually see stuff up to 10 millimeters, which is pretty impressive. And this is the 990F towed side scan system. This is how it works. You can use either both scanners or you can use just one of them. Generally, when we're doing structures, we just use one. You end up with a sweep right across, as you can see on this on this diagram here. And the sonar connects to the top box, which is like the electronics. That connects to the power source, and any Windows laptop or PC with a USB connection to display, record, and playback digital sonar images using the Starfish scanline survey. So we tried it out on the scale of the River Wyvern training wall at Oxford on the A34. And as we can see here, debris can cause the entire hydrodynamic design of a structure to alter in hours, causing severe and unexpected consequences very quickly. After the winter storms, the training wall was observed to have been backscoured by eddy current action after a tree fell in the watercourse, partially blocking it. This was only after 14 hours of flash flooding event time. During severe weather and flooding events, water structures in Area 3 were inspected daily to maintain adequate safety margins for the structure and its users. Anyway. And this is the side scan image of the wall. Actually, if you just go back, you can see that the wall is made up of these concrete planks with a capping beam, and they're sort of tongue and groove planks. So a bit further out in the river, we can see here planks. You see the gaps in the planks. Any space that isn't filled is on side scans shows up as a shadow, basically. And here is a plank with gaps either side indicating a slight displacement. And here are planks with no gaps and no displacement on the bottom, and that's a bit better. So we can see the outline of the planks on the river trailing wall. Also, there is a displaced plank that could cause the undermining of the abutment wall itself. Now, once an anomaly is identified, a surface supplied air diver will be sent to the exact location, significantly reducing risk, time and cost. There is no longer a need to laboriously fingertip search a structure anymore. With high definition side scan equipment, poor water visibility is of little consequence. In this instance, the plank was found to be slightly displaced and leaning forwards. This can be monitored on subsequent inspections and the side scan traces compared. Side scan image of two uncharted subsurface outfalls in the River Avon, and this is in Ringwood under the main road there. So these drainage outlets were not on the structure drawings and were causing significant trenching next to the structure, as you can see. This was unrecorded until the side scan results were examined. So very significant problems and completely undetectable by normal inspection, even when the water's quite low. So the lessons learned from the trials and operations. So the unit worked just as well in heavy silting conditions when the water had materials in suspension. One unexpected effect of the high frequency of the unit was that it sees straight through light weed growth and gets an echo off the structure beneath, allowing inspectors to accurately assess the condition of a structure in a single pass, and then send data straight to the defect, reducing risk, time and cost. The unit cannot give a good image where there is any air entrained in the water, such as close downstream to a drop-off or weir, or debris causing cavitation and hence air in the air bubbles in the water. Because it relies on passing the signal through a solid, which is the water. Any air, you just end up with like a snow. When mounted in a rigid frame off the side of a rib, the rib had to be driven at a constant angle, so no skidding or crabbing was taking place that would cause the unit to cavitate and lose resolution. The colder the water, the better the image was, as water density temperature made a noticeable difference to the sharpness of the image. And there is no longer any need for structures to collapse from scour, as they can be monitored in real time. We had a manned rib and we had a remote controlled rib. So if the water was rough, we just used the remote controlled rib with the side scan unit hanging off the side. So, flooding to Winchester. And here's a picture of the crypt in the cathedral. In winter 2014, Winchester was threatened by catastrophic flooding. Many areas of the city started to flood, and the Army, Fire Brigade and residents fought to control the rising floodwaters entering the city. Disaster and mass evacuation were only days away when Area 3 were approached by the Environment Agency to see if there's anything that could be done to partially dam the river reaching bridges where they cross under the A34 and the M3. Area 3 engineering staff worked for 26 hours straight to carry out the calculations to ensure that the embankment loads were not exceeded by the water pressure in the proposed water pressures. 10 square miles of farmland will be deliberately flooded to a depth of up to 2.5 meters to the east of both bridges to buy some time for the water levels to drop in the city. Highways England surveyors shot transits from both proposed dam sites the next day to determine the height of the dam that would need to be, and 500 one-ton aggregate bags were filled by a maximum 24/7 effort using all available assets and contractors of Area 3, including assets from Army Royal Engineers who shipped and placed the one-ton bags to form the dams, and they were transported to the dam sites by tank transporters because they could carry a colossal load. They also supplied the cranes and the staff to place them. So the A34 southbound was closed at 1900 that night, and the aggregate bags, and this is the A34 southbound here, were loaded to position by 3 mobile cranes supplied by the Army. The Army assisted in transporting the bags with tank transporters. By 11 a.m. the next day, both A34 dams were in position and water levels had already started to decrease in the city. 3 days later, the M3 southbound was closed. The River Itchen Dam there as well, which is dam site 2, which is just over here. See, there's 1 and there's 2. As well, when the water started to overtop the first dam site of 1. So it only took 3 days to flood a huge area, and then as it started to overtop, we then dammed the motorway bridge. It was probably a bit easier and less risky for us, the motorway bridge, because it was a more modern piled structure and wasn't really affected by scouring in the way of these Kingsworthy bridges were, which were just founded on river gravels and chalk. In this way, the city was given 6 days relief from rising water and disaster was averted. Thankfully, it stopped raining. Had it not stopped raining, it would have just delayed the inevitable. The operation would not have been possible without the new sonar techniques developed by Highways England with partners CTEC that allowed real-time monitoring of the A34 bridge abutments for scour from a small rib equipped with the sonar equipment. Aggregate bags were adjusted each night, and the scour was monitored every 6 hours by CTEC divers operating the rib. And I can't tell you how important that was. The Highways Agency were prepared to lose both of the A34 bridges to stop the flooding in the city. That was a given. And but fortunately, because we developed this new technique, we can monitor in real time the scour of the abutments, and every night we move the bags around to reduce that. And that worked really well. And here are the guys in the Royal Engineers placing some of the bags. You can see the water depth there is probably 2.5, 3 meters, and he's standing on top of the bags. So yeah, absolutely brilliant. They trained for this, and as soon as the call came in, we had soldiers there very, very quickly, and I can't say what fantastic professionals they would work with. They were just brilliant. So Army Royal Engineers placing the aggregate bags that will form one of the 2 dams at the A34 Kingsworthy 1 and 2 river test bridges. Army engineers carried out this task as we did not have the appropriate training or experience, and the Army were trained in disaster relief methods. Area 3 contractors filled the bags in a 24/7 effort. Similar dams were created at the M3 river test bridges. The M3 bridges were modern pile structures that did not require full-time monitoring, unlike the A34 structures whose abutments were founded on river gravels and hence very vulnerable. Here's the guys monitoring from the rib, and here's where we released the floodwater. The actual floodwater came within 1.5 meters of the top of that arch. The actual A34 southbound there is an old railway embankment, and the road's just plonked straight on top of that, basically. So, so fortunately, it's nothing modern. It's been there for a very long time, since 18-something. So it managed to withstand the battering from water. I've got another time we're in Newcastle. They also were part of this group that would do experiments with the Tritech side scan sonar funded by the Highways Agency at the time. And this was one they produced of the Newcastle dock walls, which is just incredible. Managed to stitch the images vertically together, and before we did this, no one had ever seen anything like this. It was like totally new. This is a railway bridge found in the river. And you can see the resolution on this is just fantastic, really, really good. So you can see some slight gaps here that may need pointing. And again, at times of low flow and decent weather, we can go down there. Divers can do that no problem. And yeah, just monitor these. Again, that's tidal wave marine. Okay. So in Area 3, we also use the video array ROV system to record images in flooded confined spaces. 3 service culverts on the M4 in Slough were surveyed by ROV as divers could not access the culvert due to small manholes, not allowing a fully suited surface air supply diver room to climb in. Each of the 3 service culverts, and these are in Slough, contained as much water volume as an Olympic swimming pool. So pumping them out was a 3-day operation if you were lucky, and where the hell do you put all the water? That's just a massive problem. So the ROV this ROV was also equipped with BlueView's 2250 multi-beam profiling sensor, which is like this spike on the end. And what that does, it gives you a point cloud, complete circular point cloud. And I'll show you some images from that in a moment. So with a video array ROV, all 3 culverts were inspected in a single day by CTEX diver ROV technicians, and high quality images obtained of their condition. This ROV was equipped, as I said, with T20 multi-beam profiling sonar as well. I'll show you some results of that. It's just an amazing piece of kit. And this is what BlueView can give you. And this is a flooded tunnel, I believe it's from Norway, from a dam. And it's just a tunnel carved out of the hard rock. So ROVs and autonomous vehicles, AUVs, and an autonomous vehicle is a vehicle that uses the multi-beam scanning sonar to also navigate. And it can be pre-programmed to do various things. So they carry multi-beam scanning sonars that can not only create a high-resolution point cloud like this, but can also be used to navigate the vehicle in real time in cloudy water where there is poor or no visibility in pipes and tunnels. BlueView's 2250 multi-beam profiling sonar is specifically designed to produce high-density 3D data to centimetric accuracy. Using high-frequency, low-power acoustic multi-beam technology, the system uses 2,100 overlapping narrow beams to create a continuous 360-degree profile, which is streamed to Teledyne PDS software at a frequency at over 20 Hz, creating a point cloud from which a truly detailed analysis of the health infrastructure can be made. It's designed for use on ROVs, but with a built-in data logger, making AUV, the autonomous vehicle deployment, equally straightforward. 2250 allows inspection companies to use the existing ROV technologies to map tiles in fine details without the risks associated with dewatering. You can see it's pretty impressive. There's another flooded tunnel. Again, this is a bypass tunnel for a dam in Norway. It's always flooded. All they did was to stop the flow in the tunnel with the valves, and then the ROV, the AUV in this case, can swim straight through it. You get a fabulous view of that. There's another image from a flooded pipeline that we took, and that's just some debris inside a pipe, which is probably about 2 meters, but it's in a bit of a state really. But again, it's very difficult. You know, a diver wouldn't be able to go in there; it's just too small. Did anybody lose a bike? Thank you for listening, and I hope the subject matter was not too dry for you. Any questions?
Thank you, Mike. Before we go online, any questions in the room for Mike following that lecture? It's the second time, which is the second time.
I want to know what Area 3 is.
Yes, I would say, highways, I don't know what it's called this week, it's not Highways Agency anymore, is it? It's National Highways Area 3. It's all of the M27, all of the M3, up to the M25, the M4 between Slough and Swindon, and the M4 and the A404 and the A404M. So big, and also the A3, 8, and the road currently down through Greenway, yeah, all that, yeah. But only up to the M25, that's as far as we go. So it's a huge area, really. And that's, I was inspections manager for that area, and we had 2,260 structures to look after, which is a lot of structures. But like a lot of things, they varied from stuff built in 18 something or other, with hot riveted iron beams, to really modern structures which were built, less than 20 years ago. So there's a good variety of stuff there. We had, lots of really interesting stuff to do. But again, it's very, because of the variety of construction and types of structures, the history of the structures kind of denotes how quickly you have to action them. But as a general rule, all the structures were inspected every single year by skilled structures operatives who used to maintain them every year, visit every structure every year. Every second year, they'd have a technical inspection by an engineer from ground level, and that was generally at the time they were being maintained as well. And that was every 2 years. Every sixth year, we would have a principal inspection, and that was every piece of the structure from touching distance. So it was basically it's a high reliability system that ensures that the structures never really get out of hand, and you can spot the stuff early. And we don't generally have bits of concrete falling off bridges. We generally get there first. We had the Federal Highway Administration visit us not long after we'd done this, which is a bloody thing. And they were, we had worked with them before actually, because they taught us how to heat straighten a bridge which got hit by a piling rig. And they came and taught Maybes, who are our main contractors for steel bridges, to do heat straightening, which was it's part science and part black art. We were the very first people to do it here on a structure, on a bridge anyway. Obviously, this is something that's done in a shipyard on a daily basis. But yes, that was really cool. So we had a relationship with them anyway. And then when the big bridge collapsed, I think it was in Illinois, and that was inspection issues, they came and worked with us for about a month, updating their systems to reflect exactly what we were doing. So stuff didn't, get out of hand. But I can't remember how many structures just in Illinois they had, but it was like 9,400 or something. And that was just like a very small bit of, it was just incredible. So the problem that they had was just enormous, but we gave them the tools to deal with it, and I think it's certainly helped. There's no bridges collapsing since then. So.
And you've given us a lecture on that subject. Like, is it part of one of your?
Yeah, probably is. Yeah. It's part of the VRS lecture.
They're very interesting. Lots of interesting pictures.
Yeah.
On that. Hopefully you can deliver it again.
Yeah, another time. Yeah. But anyway, so I was very fortunate. The people who were in charge, a guy called Guy Beresford at the time, who was in charge of Area 3, he was an ex-lifeboat coxswain, so really understood everything to do with water and the dangers and stuff like that. And he was really keen to do this and supplied about £80,000 of funding to do it. And we delivered that for him. And it made a massive difference. I mean, we did the River Handball Bridge, which is 2 massive caissons in a very fast-flowing dynamic watercourse. And at high tide at the stand, we ran around it twice, both the caissons, went away, looked at the imagery, and then came back the next day at the stand, and there were 3 problems with it. The whole thing was covered in weed. So we knew where they were because the Tritech sonar, because of the super high frequency, sees straight through like weed growth. It's really weird. It's like you just place a shadow over it, but it's still there, you can see through it. Anyway, we sent the divers down, it pulled a bit of the wheel away there. It was exactly where it was. It was just absolutely mad. That was completely unexpected. I didn't expect that. One of my neighbours, a sonar scientist and used to work with the MOD, and he helped us with some of the technical stuff. He had to be very cautious about what he told us because, what we did here was like light years behind what they were doing. And but without his help, I think we would have never really got to the point we did. So that was great. Anybody got any questions?
Anybody online have any questions? So we'll come back to the room. Online, anybody wish to ask Mike a question on the lecture or anything in general? Quite a knowledgeable chat.
No, it's very good, Mike. Thank you.
Thanks, Tris. Yeah, so inspection in terms of maintaining safety is super important, especially for structures. We all saw what happened to that bridge in Italy, in Genoa, when it collapsed, killing hundreds. And that was an inspection failure, pure and simple. And
Can you give us a lecture about that one?
Possibly.
I'd like to hear about that.
So are you saying that bridge was built properly, but then just not inspected?
Correct. It wasn't maintained or inspected. The design had problems, and it probably, in terms of modern codes, the bridge probably didn't have enough redundancy in certain areas, but had it been inspected properly, that wouldn't have been too much of a problem, because it was spotted those problems early enough to deal with them. So it's just very, very unfortunate. One thing that Highways Agency at the time did, when they renewed the contracts and made them kind of a reactive contract where you would do, where if there's a problem, you identified it and you went and fixed it, the bridges were never ever put into that. They were always sat outside of those in this super high reliability inspection regime that basically had its own budget and stuff like that. They were never, there was always traffic management available to do it. You didn't have to wait till they put something else on. And that was auditing with structural safety. So we're quite lucky in a way, but I did sit down with head of Highways Agency at the time and said, you must not include the bridges in this because you'll end up with bridges falling down and people getting hurt. And to be fair, they took notice and they never put it in, and it isn't in to this day. It sits completely separate outside of the contracts as a separate entity, because that's the safest way to do it.
Any other questions? Silence.
With the ROVs and the tools that they use then, how do they know where they are? Is there some sort of local GPS that they use?
Yeah, so what happens is, there's two sorts. We used mostly the video rate ROV, which was a tethered vehicle. So we were putting it into a relatively small space. So the culverts under the M4 were about the same size as this room, but probably 4 times as long, full of quite clear water. We did have the multi-beam sonar as well, because when you first put it in, you're not really sure as you go in what's actually going to be disturbed when you swing around. And if the water starts to go bad, you can't see, but the multi-beam sonar just sees straight through that, and you get this point cloud you can navigate by. And there was all sorts of pipes and stuff like that. There were several that we used the ROV to do. We used the ROV on there was another flooded culvert by Harwell, where they had the nuclear reactor. And we used to look after the culverts that supplied both sides, again on the A34, that supplied water and electricity to that facility, because it had to be absolutely super high reliability. It could never ever be allowed to be turned off or compromised. So we used the ROV for that, and we actually used to, because of the risks from nuclear accident, if anything went wrong, we actually inspected that with ROV every single year. So yeah, it was great. It was good.
Fantastic. Yeah, any other questions? Online, any questions? Speak now. Okay, unless anybody interrupts me. Thank you, Mike, once again confirming my choice to appoint you as CPD lecturer. Come to fruition again. Well done.
Stop sharing.
And so we'll call the flaps, Mike. I think that's a round of applause. Can we get the agenda up, please, John? So I don't know about events, but while I'm waiting for the agenda to come up, this is the last meeting of 2022. The next event we have obviously is a Christmas party, which I mentioned earlier. We'll be back in for meetings in January, and it will be the 4th Thursday, which I'm sure John's put up there, the actual date. What is the 4th Thursday?
26th of January.
So we'll see you all again, hopefully, on the 26th of January 2023. And our CPD for the evening is to be confirmed.
It is. I've already approached a company, as we've had this discussion before, because Scott and I have both done a bit of plate bonding to structures to strengthen them. I've done a little bit on the M3, and Scott's done some also further away than that. But I made contact with a company that does carbon fibre plate bonding, and they said they're going to come and give a CPD about it, which I thought would be super interesting.
Yes.
So they do carbon wrapping to vulnerable structures. They do carbon wrapping to stop bursting from vulnerable piers and all stuff like that. So I thought we'd definitely like to hear about some of that.
Yeah,
Very
so
interesting.
for those of you who don't know, carbon fibre reinforcement is well, it was probably about 10 years ago, was the new tech. It's not widely recognised or used, but it is a very incredible technology. It's amazing what it can do at such light weights. So I'll be interested if you get that mind.
Yeah, looking forward to that. I'm going to probably try and give them a ring tomorrow and arrange a more detailed phone call for next week, so we can actually flesh out what exactly. But the stuff they sent me was just absolutely amazing. Some of the stuff they do is incredible. Where we used to do steel banding around vulnerable piers under bridge bearings to seismically protect them from bursting.
Yeah.
They'll just go there and wrap your carbon fibre super quickly now. It's
Glue it on.
It's absolutely amazing. What they can do is just incredible. And they can also, unlike steel, they can wrap very complicated structures and shapes. And that's really, really brilliant. So, another person I want to thank was Dr. Chen, who helped me tidy this up a bit. It's not quite the thing you had seen before, and Sarah worked quite hard in tidying it up to make it a bit more presentable. So thanks for that, Sarah.
So you gave her homework, is that what you're telling?
Yeah, she volunteered.
Thank you, Sarah. Next time he's overreaching, let me know. Anyway, I can't see this thing.
What do you want to know, Scott?
What I want to know is, just let me know that's it, and I can wrap the meeting up.
That's it.
Right, okay, so we'll see you all at the Christmas party. If you wish to attend, just remind you it is self-funded, it's £10. It's on the 8th of December, and Tom Barnett is the one to contact. He will be sending out an email soon. If you do not receive an email by Monday, ping any of us and we'll forward you on the details of the Christmas party. Thank you very much. The meeting is now, as an hour into the meeting, that's perfect. So that's 1 hour of CPD.
Thanks for coming in.
That's it. Very much, everybody. I'll close the meeting.
Thanks, everybody.
Thank you.
Thanks very much.
Thank you. Thank you very much.
Cheers, Al.
Thank you.
Thanks.
What was the online numbers there?
Thanks, gents. Cheers.